Swayam Prabha. Digital India. Educated India.
Welcome to this course on transition metal organometallics in catalysis and biology. We have been talking about olefin polymerization, and in this context we have covered lot of grounds, particularly with respect to homopolymerization. We started off with ethylene homopolymerization with using Ziegler-Natta system, as also moved on to propylene homopolymerization with the Ziegler-Natta system, then to metallocene system. Then we had seen advent of MAO and boron based reagents, metallocene catalyst, which were extremely active for ethylene as well as propylene homopolymerization. We had also observed how the stereospecificity of the polypropylene polymerization could be controlled using a variety of metallocene catalyst, and then subsequently in the last few lectures we have moved into copolymerization reactions of these olefins, and to this extent we have looked into copolymerization of two different kind of olefins. For example, diolefins, one can be ethylene, the other can be alpha olefin, as well as we have also looked into copolymerizations of cyclic olefins, which are which could also be used. So, in this context we have spoken about one type of cyclic olefins which were obtained in the previous class, which was obtained using two reactions. One is one is Diels-Alder reaction followed by copolymerization of the cyclic olefins. So, let me just focus on what we had finished in our previous class, and then we want to move into the other routes of making this kind of cyclic polyolefin polymers. They can be formed by two ways: by two methods, and these are really a very interesting method. The one we had discussed in the last class involves two reactions. This is method 1. Or metallocene catalyst, and that could give that could give this polymer of this type. So, we had seen how these polymers are important for magnetic applications, and we are going to now take a look at the other pathway using zirconium catalyst. The second pathway uses in the zirconium X2 MAO catalyst, and the reaction is shown over here. So, it already has a polymer chain building on it, and then this olefin comes. The first is the insertion of this olefin on the metal polymer chain length, and then that gives this inserted product. Now, then what happens is the first this is called intermolecular insertion, and now intramolecular insertion would happen. Now, this will now insert in this bond to give this product, and subsequently this insertion would follow through. So, there are two types of insertions, and that would give rise to various kinds of products, possible products, which are shown here. It can be this where the stereochemistry can be meso within the ring or racemic, M is capital M or small m for meso, R and smaller for racemic. Like this. So, this is cis isotactic. The other possibility can be like this. So, where it can be R, 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 R. So, this is trans isotactic. Similarly, it can be M R, M R, M. This is cis syndiotactic. Cis syndiotactic, and the last can be and this can be R, M, R M R, and this is called trans syndiotactic. So, these insertion can happen in 4 ways as is shown over here, and these are 2 types of insertion as has been mentioned in this. So, one is intermolecular, the other is intramolecular, and these gives optically active polycyclic olefins, and the best one which is produced by this method exclusively is trans isotactic. So, this is the one which is exclusively produced, this is the trans isotactic. So, this is an interesting result. We had seen that there are 2 ways in which polycyclic olefins, one can be through copolymerization by Diels-Alder and then using the vanadium catalyst, the other can be using a non-conjugated diene and doing intramolecular and intermolecular catalyst with chiral answer bridged zirconium zirconocene catalyst. So, that exclusively gave the trans isotactic products. So, apart from this there are several efforts were made in trying to diversify the metal, and in this regard the emphasis were developed on generating non group 4 catalyst. And in this regards the several metals were looked into, but what emerged out are these lanthanodcn, lanthanum derivatives are called lanthanodocene, and other metals, other transition metals like iron, cobalt, nickel, and palladium became of interest. Now, when the quest for other types of metallocene were developed, then this lanthanum based the catalyst as well as other transition metals like iron, cobalt, nickel became of interest. So, developing, so we are going to focus right now on the first part, which is this lanthanum based metallocene catalyst, and the question was there was a nice work by Watson who sort of developed. Watson reported Cp star 2 Lu methyl complex for ethylene polymerization. So, but this is an interesting complex. There is the Cp star complex. The complex could take ethylene and like polymerize it fast polymerization, to give Cp star So, it could successfully polymerize ethylene very fast, but the interesting thing is that it could only do one insertion, single insertion with propylene. So, with propylene it could first give this alkyl complex, and then the second ethylene of insertion was surprisingly very slow to give a slow complex of this type. So, and beyond this it did not proceed, and then this is a very unusual behavior in terms of the earlier observation that only one ethylene insertion and could take place and the reaction did not proceed. So, and then the thing which was contrasting is that corresponding metallocene complexes for zirconium could allow several insertion of propylene to give the product, and this was finally explained by Ziegler using DFT calculations, which sort of said that coordination in the neutral alkene zirconocene cationic zirconocene complex is more favorable for further reaction than in the neutral lanthanum species. So, this is explained by Ziegler by DFT calculations, and DFT showed the isoelectronic species are structurally different. That is, for lanthanum it is a neutral compound, whereas for zirconium there is a approach of olefin that could bind. For zirconium, because of this cationic nature, there is a free site where it could bind, favors alkene binding, and these for the lanthanum series, because it is the isoelectric which is neutral in nature. So, they are less favorable to alkene binding and favors dimerization, favors dimerization with formation of mu r species. So, there is a fundamental difference between the lanthanum complex as well as the zirconocene catalyst, which could polymerized olefin, and the reason was finally answered by DFT, which sort of showed that this is a neutral complex, this is neutral and this is cationic. And being cationic, it favors olefin binding, whereas this neutral, these does not favor olefin bonding to a great extent. On the other hand, there is a decomposition of the catalyst through formation of R alkyl bridges is observed in cases of lanthanums. This was a great difference between the lanthanocene chemistry as well as the transition metal zirconocene chemistry. In case of lanthanocene, alkyl compound sigma bond metathesis is also observed. Another interesting reactivity of lanthanocene catalyst is in case of lanthanodosine alkyl compound. Instead of polymerization, sigma bond metathesis reactions were reported. And this and of the first in this is the insertion into the alkene bond as is shown to give the corresponding species that in presence of another propylene gave this sigma bond metathesis reaction to give the compound which is this, and for yttrium also plays a role, and then several metals of this type, for example, scandium, yttrium, lanthanum complexes are also reported to exhibit this polymerization activity. However, these catalysts are yet to find practical utility. However, these complexes are yet to find practical utility. Now, these are starkly different in terms of behavior with respect to the early transition metal zirconium catalyst, and the main thing what we had seen that though they may be able to polymerize ethylene, these cannot undergo subsequent propylene insertion, and in some cases only one insertion of propylene could be obtained, and in other cases even that is not observed. Just after first insertion, the second insertion does not happen, and just sigma bond metathesis reaction takes place. So, with this we come to the end of lanthanum chemistry for designing polypropylene catalyst as a part of these non group 4 transition metals, non group 4 metals for polymerization purpose. And now we move on to the effort that describes other non group 4 metals in catalyst, and they involve other transition metals, for example, iron, nickel, cobalt, palladium, so on and so forth. Now, the story is sort of first focuses on iron by a catalyst given by Gibson, Brookhart and Gibson. They are fantastic catalysts, and then the focus sort of from lanthanum shifts to iron. Age of polymerization. And these are two like a very important catalyst is given by where R is a bulky group. Is equal to isopropyl or bulky group. This with MAO and MAO greater than 300 equivalents, and in ethylene when R equals methyl, this is R and R dashed, two different substituents, this is R dashed, R equals methyl, R dashed equals hydrogen, it could give oligomers alpha olefins C10 to C20, and when R equals R dashed equals methyl, then it could give H high density HDP, high density polyethylene. High density polyethylene, and this is activities. The important thing is the activity of is very similar to the activity is comparable to most active Ziegler-Natta catalyst. This is a important discovery in the sense that the iron right now can be used to produce oligomers as well as ethylenes, high density polyethylene of extremely high activity. With this we come to the end of today's discussion, where we have looked into development of non-group 4 metal based catalyst for olefin polymerization, and now we have seen that how the landscape changed on going from lanthanum to iron. So, more of these non group 4 transition metal catalyst as we take up the discussion in the next class, in which we will move beyond iron and see other metals like nickel, cobalt, so on and so forth being present for these developing polyolefin polymers. So, with this I again thank you for being with me in this class, and I look forward to being with you in the next class, where we take up these non group 4 transition metals in more details. Thank you.